which of the following molecules is more stable? So right here, we are looking at a molecule known as 2,3-dimethyl cyclohexane. That is a one big long word, but it tells us we have two substituents here. Ooh, not 2, 3. I'm going to say 1, 2. Not even 1, 2. I'm going to say 1, 3. Long day, guys. Stay in school. All right. So we have a methyl group on our 1 and our 3 positions. So if we go ahead and label that, that will help us locate where this is on our cyclohexane chair that we are going to draw for visualization. Now, it is very important to draw our chair conformations, especially if we're on an exam. This could really help us out here. Ignore how ugly it is. Now, I'm running out of room, but if we draw our happy little chair conformations. All right, that one's not ugly. All right, that one's not ugly at all. It can help us see which one is going to be more stable. Now, let's use red for our axial positions. Now, I like to think of it as up, down, and that will help you visualize which one is going where. And for our equatorial positions, we will use, it's a hard position to draw. All right, so that one's kind of up. This one's also kind of up too. We'll use blue for our equatorial. Now, remember, up, down, up, down, up, down. Just keep repeating it to yourself. It will really help you visualize which one is going where. So when we draw our molecule like this, right, you have to remember, if one is up, the other is down. All right, so now that we have these, let's go through and add our 1 and our 3 carbons. 1 and 3 methyl groups. So let's say I choose this axial position right here. Great position. That one's going to be up, and this one's going to be up. And we know that because this is cis. It's going the same way. Whereas over here, our molecule B is trans, because they're going to be facing different ways. You can tell that because one's up, one's down. Well, we'll get to that later. But let's focus on A. Both of them are facing the same direction. So, over here, that is up for us. Whereas in our flip chair position, that means it's down. No, not down. No, still up, just in our equatorial positions. So up, 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 up. Up here, up here. Except over here, these ones are axial. And what's going on with our large substituents here is they have hydrogens. And that is going to cause a lot of steric hindrance. We don't want that. We don't want them. They're clashing. That's not stable. That's going to be high in energy. We want our low energy cyclohexanes, everyone. All right, so if we draw our hydrogens here, see how they're all not clashing with each other? It's because equatorial is more stable. We love our equatorial. So for this molecule here, it is the most stable in the equatorial position. Now, what about molecule B? Well, it's still in our 1,3 position. And so what if it's trans? Well, that actually has a lot to play. If we go ahead and we draw our chair conformations again. Oh boy. Looking a little bad here, but you guys can't judge. Alright, so if we go over here, and let's have our first one be in the upwards axial position, right? Well, that's axial. We don't want our substituent in axial, but our next one is down. In the equatorial position, by the way, everyone. This one is axial. This one is equatorial. Okay. Now, what if we flip the chair? Okay, maybe this chair conformation just isn't suiting us. Let's take our molecular modeling kit and flip it. So now, what was up over here in our axial is still going to be up, but it's going to be up in our equatorial, right? And then if we go to carbon 3, what was down before in our equatorial is now going to be down in our axial position. And when you look at that, the steric hindrance produced by the axial positions did not go away with the chair flip. There is no one stable conformation. Both of these chairs are equal in their stability, whereas if we go to molecule A, the chair on the right is more stable because you have both of them in equatorial position.